and in 1 and 2 dimensions. So chapter 9 is kind of a long chapter, and that's why we're splitting up into 2 sections. But it's based pretty much on one idea, which is if you have no net external force acting on you, then your conservation of your momentum is the same for if you consider all internal particles. Now this wasn't true in this case because we had external forces here, such as friction, acting on me, and so we were not able to do this as I had hoped. But let me show you basically what this is based on. So if I just look at F is equal to dP dt, and I say dP therefore is equal to the integral of dP is equal to F dt, but if F is 0, then P final minus P initial, right? If I just integrate this, P final minus P initial is equal to 0, means that P final is equal to P initial. So as long as we don't have any internal forces, any external forces operating on the system, then our initial momentum is going to be equal to our final momentum. And basically, if we would have seen, if those skateboards had the same rolling friction, which is essentially 0, so we have no external forces operating on it, then if we started off at rest and started pulling towards each other, the momentum would be the same. But that's because Gary and I, weighing the same amount, would have had opposite velocities in the direction of our velocities would have been opposite, and so our momentum would have, the net momentum would have been 0. So our initial momentum would have been 0, and our final momentum would have been 0. And in the collision as well, what should have happened is Gary would have collided into me, and then I would have moved on, and Gary would have stopped. But we'll see that mathematically today. Maybe we'll get a new skateboard. Okay, so now, so let's talk about 2 types of collisions: inelastic and elastic. What is an inelastic collision? Anyone know? Yes.
Inelastic collision is a collision where the momentum is not conserved.
Okay, momentum is conserved. Energy. So energy, for example, if Gary had rammed into me and suddenly it had made an explosion, right? Not so bad, but the energy would have been transferred into heat, into sound, into various other things. When a collision is elastic, a completely elastic collision, all energy is transferred from that in the collision from the initial state to the final state. So the momentum in these collisions, as long as there aren't any external forces, is conserved. But the kinetic energy in elastic collisions is conserved, but not in inelastic collisions. So we're going to only consider the 2 extreme cases of these today, which is completely inelastic and completely elastic. However, most of everything that we observe in real life is somewhere in between. Okay? We can get pretty close to being completely elastic. For example, if you play billiards, that's pretty close to being an elastic, completely elastic collision. And inelastic, for example, is if I took a ball of putty and I threw it another ball of putty and they stuck together and they went off. Okay? So we're going to consider these 2 cases. So first of all, let's consider completely inelastic collisions. So what is completely inelastic again? There may be one starting off at some velocity, something is at rest, for example, and they come together and they stick. Okay? They stick together so that the two particles move together when they leave. That's completely inelastic. Okay? So, let's just consider a stationary target. What that is, for example, I have a particle which I'll call mass 2, and then I have a particle which I'm going to call mass 1. This one is moving with some velocity v, which I'll call v1 initial. So we need to keep track, because in these there could be up to 4 velocities in the two-body collisions. There could be a velocity initial of mass 1, there could be a velocity initial of mass 2, and there could be a velocity final of mass 1 and a velocity final of mass 2. So we're going to keep track of, we're going to call this v1 initial, just meaning that this is for particle 1, and it's the initial velocity of that. That's what those subscripts do. Okay, so this is at rest, and so v2 initial is equal to 0. So this is a stationary target. Now what's going to happen in this scenario is that mass 1 is going to hit mass 2, and then it's going to move off together. So what would be the initial momentum of this system? Sorry? Okay, so what is the momentum of the first mass? Okay, so this would be mass 1, v initial 1. Okay? Now, what would be the okay, so this is all right. So this is the initial momentum of the system. What would be the final momentum of the system? Yes. Okay, so it's going to be mass 1 plus mass 2, and then we'll just call it, in the book they call it big V. Okay? So you can call it V1 final, V2 final, but since they're moving together, we'll just call it big V. Okay, so big V is therefore just going to be equal to M1 V1 initial divided by M1 plus M2. Okay, now if I were to take the velocity of the center of mass here, what would the velocity of the center of mass be? How do I find the velocity of the center of mass? Let's just look at the velocity of the center of mass before the collision. How do I find the velocity of the center of mass? I have M1 V1 initial plus M2 V2 initial all over M1 plus M2, right? That's how we find the velocity of the center of mass. But what was V2 initial? 0. It wasn't moving. It's a stationary target. And so we see that this is M1 V1 initial all over M1 plus M2. Does this look familiar? So the velocity of the, if you look at this, this is the same as the velocity of the two joined masses now after, and it's the same as the velocity of the center of mass before the collision. In other words, the velocity of the center of mass does not change after the collision. Right? This is the velocity of the center of mass before the collision. This is the velocity of the center of mass after the collision, but it's also the same velocity with which both of these particles leave together. Which makes sense, right? Since now both of them are moving together, you would expect that the velocity of the center of mass would be the combined two particle velocity. Questions? It's kind of a neat thing if you think about it, right? The velocity of the center of mass is conserved through this whole process, and that's basically another way of saying that the momentum is conserved. All right, so let's do an example. They have an example, for example, this is called the ballistic pendulum. So one of the ways that you can determine the velocity of a projectile, or for example, a bullet, is simply taking that bullet into a basically a hanging block that weighs a lot. So for example, let's suppose this is 5 kilograms in mass, and let's just say this is 10 grams. Now, when this bullet hits this block of wood, it's going to stick in the block, and then this will swing up to a certain height. And then once you know the height that it swings, then you know you can determine the speed at which this moves. So this is the before, right? This is coming like this. This is the before picture. And then this is the after, which is the bullet's now lodged in here like this. Okay? So this swings up like this. So how would we go about solving this problem? This is essentially a two-part problem. So how do we go about solving this problem? Any ideas? Yeah. Okay, so we can first start off with the momentum of this bullet. Then so what we're going to do is break this down into two parts. First, we're going to say, what is the momentum of this bullet before? Then it's going to be lodged in this block of wood. Then we're going to find the momentum of the total system. Then we're going to change this from kinetic energy into potential energy as this goes up. And we're going to assume that once it gets lodged in that block, then the kinetic energy is going to be transferred all into to potential energy. Yes?
So is this elastic or elastic?
This is completely inelastic. And it's completely inelastic because of the fact that these start off as independent masses, but then become a single mass moving up like this. Okay, so inelastic, completely inelastic means that you start with two masses. After they collide, it goes into a single mass, moving at one speed. Completely elastic means that there is no loss in kinetic energy during the collision. Okay? Yes?
If it's inelastic, how do you know kinetic energy is conserved?
Kinetic energy is not conserved in an inelastic collision. But what I'm saying is, you're going to have this come in here, it's then going to be moving. So I think the question that you have is, what about the kinetic energy of this bullet? Right? Because the kinetic energy of the bullet has some value. Does that kinetic energy of the bullet get transferred up into the mechanical energy of this two-part system? And the answer is no. So what happens is, what I can do is I can use conservation of momentum when the bullet and the mass collide, that conservation of momentum then gives me a velocity of this two-body system. And once I have that, that's the kinetic energy in and of itself. Now I have the velocity of the two-body system, and then I can change that kinetic energy into potential energy. That answer your question?
Yes.
Okay. Okay, so first of all, we say that M1, V1 initial is equal to M1 plus M2 V. Okay. So we know the initial momentum is M1, V1, but then that goes into a two masses sticking together with a single velocity V. And so V is equal to M1 V1 initial all over M1 plus M2. Now, what is the kinetic energy of this two-mass system? How do I find that? Yes? Okay, so I have 1/2 M1 plus M2. That's someone's phone?
Sorry, it's like stuck over here.
Aha. Sound like a drill or something. That's all right. Okay. So then I get M1 plus M2 GH. So what I'm going to say is all this kinetic energy is therefore going to be transformed into potential energy. Now let's assume that this final height is 10 centimeters. All right, well the first thing we see is the mass 1, mass 2 cancels out, and I see that V, capital V, is equal to 2GH. But I don't really know what capital V is, right? What I'm interested in is the velocity of the bullet. So the velocity of the bullet, I can then substitute in this right here. And so we see that this is M1, V1 initial, all over M1. Oh, sorry, this is V squared. Sorry, this is V squared right here. M1 plus M2. And this quantity squared is equal to 2GH. Now, just doing a little bit of algebra, I can see that V1 squared is therefore going to be equal to M1 plus M2 all over M1 squared times 2GH. And so V1 is just going to be equal to M1 plus M2 all over M1 square root of 2GH. Okay, so what we originally said was this is 10 grams, this is 5 kilograms, and a height of 10 centimeters. So let's do that all out. So I have mass 1, which I said was 10 grams, which I'm going to write that as 0.01 kilograms plus 5 kilograms all over 0.01 kilograms times 2. I'm just going to say this is 10, this is 1/10, and so I just get the square root of 2 meters. Let's see, and I get meters per second squared, meter. Okay, so I get meters per second. And now, I'm just going to approximate this. I'm just adding 0.01 onto 5 is essentially still 5. The important part is that now we're dividing by 0.01, which makes this about 500 times the square root of 2, which means that we're about 700 meters per second. So I'm going to just assume this is about 700 meters per second. There's approximately 700 meters per second. Okay? So that 10-gram bullet, causing that 5-kilogram block to rise by 10 centimeters, had to be moving around 700 meters per second in order to do that. Okay, so we just broke them into two parts. First, we found the inelastic collision, the conservation of momentum. Then once we had this, we could turn, we knew the velocity of this true mass system. That gave us kinetic energy. And with that kinetic energy, if we found that it rose 10 centimeters, then we could turn it all into potential energy. And then we could go back and find what the initial velocity was. All right. Questions? Okay, what is an elastic? It's a little funny because you have inelastic and elastic. This is elastic. We're looking at completely elastic collisions. So these are inelastic collisions. This is an example of an inelastic collision of two masses sticking together. Now we want to talk about completely elastic collisions. And I just want to emphasize, in the macroscopic world in which we live, to get a completely elastic collision is extremely hard to do. There's always some amount of inelasticity. Energy is not, there's always a little bit of energy lost. Even in billiard balls, right? When you hear them collide, you hear something, right? That hearing something means that there was energy turned into simply just audio. And so we know that there is no such thing as a perfectly elastic collision that I've seen in the macroscopic world. But when you start talking about microscopic systems, then this is a much better approximation. But we can get pretty close to being a perfectly elastic collision, or a completely elastic collision. And the one difference between elastic and inelastic is the energy, kinetic energy is conserved. Okay, so that means that m1 v1 squared, m1 v1 squared plus m2 v1 initial squared, m2 v2 initial squared is equal to m1 v1 final squared plus m2 v2 final squared. I just dropped the halves because there would be a half on all of those terms. Okay, so this is the kinetic energy conservation term. And now we also have the momentum conservation. Okay? So we can draw upon both of these equations to solve for the motion, to give us an understanding of what happens in these situations. Okay, so now let's first consider the stationary target. What we have, once again, is we have mass 1 moving with some velocity v1 initial, and then it strikes mass 2. Now this is going to require a bit of algebra, so I hope you pay close attention. Now with the stationary target, that means v2 initial is equal to 0. And this is just an easier thing to solve than both of them moving. Although that's a completely solvable problem too. So V2 initial is 0, V1 initial is just something that we won't specify yet, but we're just going to call V1 initial. Okay, so now we have two equations here, and we have two unknowns, right? We know V2 initial is, we haven't specified what V2, well we have, sorry. We've said that that's 0, and so we can get rid of these two terms. So I say that M2 V2 initial squared is equal to M1 V1 initial squared is equal to M1 V1 final squared plus M2 V2 final squared. Then, so this is the before situation. Then afterward, we're going to have M1 and M2. I'm going like this. And I should say one last thing. I didn't specify this, but we're going to do this. This is 1D collision for the moment. We will do two-dimensional collisions in just a minute. Okay, so in 1D then, we have this equation, and we also have M1 V1. Sorry, I need to slow down a bit. Okay, so now what we want to do is I want to write this equation in something that looks useful. So this is just, I'm just going to show you the algebra of how to get these equations. So I have M1 V1 initial squared is equal to M1 V1 final squared plus M2 V2 final squared. Now, I'm going to bring everything that has to deal with mass 1 onto one side and everything that deal with mass 2 on the other side. So I'm just going to bring this over here. And so I see that this gives me M1 times V1 initial squared minus V1 final squared is equal to M2 V2 final squared. Now I'm going to take this one step further, and I'm going to say I could write this as using the factoring. I'm just trying to factor this into an M1 V1 initial plus V1 final multiplied by V1 initial minus V1 final. Right? So if you do all these out, you'll see that this gives us this. Just using some basic algebra here. And this gives us M2 V2 final squared. The next thing we want to do, okay, so that's this equation, and we're rewriting it like this. The next equation is this one, which is the conservation of momentum. And so I see that I get M1, so this is conservation of kinetic energy. This is going to be conservation of momentum. Let me just write that. Conservation of momentum. This is the conservation of kinetic energy equation. So now I'm going to have M1 V1 initial is equal to M2 M1 V1 final plus M2 V2 final. I'm going to bring this over again. I'm going to get M1 V1 initial minus V1 final is equal to M2 V2 final. So now I have two equations. I have this equation for conservation of momentum, and I have this equation for conservation of kinetic energy. How would I solve for, I have two equations here, but I have two unknowns, right? I have a V1 final and a V2 final. How would I solve this? Yes. Okay, so I could solve for one of these and then stick it into the other.
Set both the equations to that entire M1 times 2y minus 5. And then by just dividing the other by b plus b minus divide both sides of the kinetic equation.
So you want to take this equation and divide.
No. I'm saying divide the conservation of kinetic. Conservation of kinetic energy divide both sides by V1 plus V final. So we get M1 times V1 initial minus.
Oh, I see. Okay, so you want to divide both sides by this term right here. Okay. Okay. That's very very astute. I'm going to show you a very simple way of dealing with this. I'll show you a different way. But basically, I'm going to take this equation and divide by this equation. Right? So if I look at this, this is an important algebra technique. I have M1, V1 initial plus V2 plus V1 final. V1 initial minus V1 final is equal to M2 V2 final squared. And then I'm going to take and divide that by M2 V2 final. And divide that by M1 V1 . Okay, so all I did was I took one and divided it by the other. Now what you can see is that M1's canceled out, M2's cancel out, this cancels with this in the denominator, so I get a V2 final over here, and I get this V1 initial and this V1 initial cancel. Okay, this is just a simple way of doing things. So what you can see is V2 final is therefore going to be equal to V1 final, V1 initial plus V1 final. Now we still have another equation. Okay? We still have another equation, we still have two unknowns, but now this is simpler. And so what we can do is we can take this equation, okay, and now we have two simple equations and two unknowns. So I can take this equation and this equation, put them together, and solve. Okay, so now I'm just going to take V2 final here. So I'm going to say this is V2 final, this is V2 final, and you divide by M2. And so I can see that I'm going to get, so if I just take this equation and solve for V2 final, all I have to do is bring M2 down here. Right? And then I can set that equal to V1 initial plus V1 final. Okay, so I have M1, V1, V1 initial minus V1 final divided by M2 is equal to V1 initial plus V1 final. Okay, so this is all just algebra at this point. V1 initial minus V1 final is equal to M2 V1 initial plus V1 final. What I like to get is V final on one side, V1 final on one side, and write it in terms of V1 initial, since we know what V1 initial is. Okay, so V1 final. So I'm going to get V1 final on one side. So if I just bring this over to here, right, then I see that I get, and right over on this side, I'm going to get a M1 minus M2 times V1 initial, and then I'm going to get on this other side V2 VF. So I'm going to bring this VF, so I'm going to get M1 plus M2. Sorry, just a bit of algebra in my head, but you can just see this. If you look at this equation, you'll see that this is what it gives. Okay? Now, if I take V1 final, So that means this is what V1 final is. So that means V2 final is just going to be equal to V1 initial plus V1 final. But I know what V1 final is because I just found it. So I get V1 initial plus M1 minus M2 all over M1 plus M2 V1 initial. If I just get a common denominator here, right, I get M1 plus M2 all over M1 plus M2 V1 initial plus M1 minus M2 V1 initial all over M1 plus M2. What you can see is that the M2s cancel. And so I'm left with V2 final is equal to 2 M1 V1 initial all over M1 plus M2. Okay, so this is an important equation right here. And this is an important equation right here. Okay, so let's do three scenarios. So the first scenario is when the moving mass is equal M and M. Let's say they're both mass M. Let's say we have a billiard ball scenario in which the cue ball and the ball you're hitting both have the same mass. Then what will be the velocity of the ball one final? So this one's moving with velocity v. What will be, and now afterward, what will be the velocity of this ball? So this comes, it strikes this ball then proceeds. What will be the velocity of ball one after they collide? Yes?
0.
0, right? Because of the fact that mass 1 and mass 2 are the same, the velocity final of ball 1 will be 0. And the velocity of ball 2, right, if we look at this, is 2m1, but there is 2m1 in the denominator as well, m1 plus m1. So I get 2m1 in the numerator and in the denominator, and so that velocity 2 of the final velocity of the ball that was initially stationary is now moving at the initial velocity of what this was. So it's like billiards, right? You play billiards, you strike that ball, hit that other ball, they're going in a straight line. The one comes to rest and the other one proceeds. Okay? And that's what these show us. Now, what if we have a heavy target? Scenario 2. In other words, mass 2 is much, much greater than mass 1. What will happen? So mass 1 is really, really light. It collides into mass 2, and so what am I going to get? What would be the velocity of ball 1? Sorry? It'll be in the other direction. Because mass 2, if mass 2 is much, much greater than mass 1, this is essentially minus m2. Right? But what's in the denominator? I have an m2. This is essentially 0. So I get m1 minus m2. This is essentially 0 in both of these. And so I get that this gives me minus v1. So a really small mass is going to hit off this very heavy target and go back with exactly the same speed that it came in. Assuming this is very, 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 very much heavier than this. Okay? So it's going to just reflect and go back like that. Okay? What is going to happen to the other ball? Or the other target? Well, in this particular case, you have M1. You only have M1 in the numerator, but this M1 is inconsequential in the denominator, and so you see that it does move away at 2m1 over m2 times that initial velocity. So it is moving away, but essentially the ratio of the mass of that small moving object to the ratio of the heavy object that was struck, the heavy target. And lastly, the scenario 3, which is a light target. Mass 1 is much, much less than mass 2. What do we have then? So mass 1 is now much, much greater than mass 2. So the velocity 1 final here is essentially just going to be unchanged. Velocity 1 final is essentially going to, this heavy mass, you can imagine a bowling ball striking a marble, right? A bowling ball striking a marble, that bowling ball isn't going to change its velocity much, right? It's going to keep on going. And basically what you have is m1 divided by m1 times the initial velocity. So you end up getting that the final velocity of the heavy object that struck it is unchanged. But there's something kind of interesting here, which is that the velocity of that marble is essentially twice the velocity of the incoming bowling ball. So if that bowling ball is moving at velocity v, then the velocity of the marble after being struck is twice that velocity. This can lead to some really interesting things, by the way. There's a, if you do this as a sequence, right? If you do this as a sequence of a heavy ball striking a medium-sized ball, striking a smaller ball, striking an even smaller ball, and you do this as a sequence, you can actually get a very small ball to move out at a very high speed. So you can get some really interesting stuff there. They have these, I forgot what they're called. You drop them on the ground and make a small ball shoot way up into the air. It's really fun to see. I forgot what those are called. Okay. Now, if both of them are moving, so what I originally described was initially a moving ball and a stationary target, and they were hitting, or a moving particle and a stationary particle, and they have a completely elastic collision. Now, the other scenario is that these are both moving and then they collide. Now, it's quite a bit, it's a bit more algebra, so I'm not going to do all the algebra out. I'm just going to show you the answer. V1 final is equal to M1 minus M2 V1 initial all over M1 plus M2, which is plus 2 M2 all over M1 plus M2 V2 initial. And V2 final is equal to 2 M1 V1 initial all over M1 plus M2 plus M2 minus M1 all over M1 plus M2 V2 initial. Now that's kind of what you would expect, right? Had velocity of the initial velocity of ball 1 been 0, this would have been what you would have expected for the velocity of the final velocity of ball 1 if velocity 2 had been moving, right? This is exactly the set of equations that we wrote down earlier for these other systems where you only had a stationary target. But you can see that they're all completely symmetric in terms of the outcomes of what we discussed over here. It's just that to actually go through and drive all that takes a bit of time. As we saw that it took a bit of time earlier, just for one week. Now the scenario becomes even more exciting when we deal with 2 dimensions. All right, collisions. dimensions. Now we're going to consider the simplest case, which is a stationary target. Otherwise, this becomes a really hard problem if you have, because then we can consider essentially the initial motion to be all in one dimension. But if you have two moving targets, then you have to consider the initial directions of both of these moving particles, which can be a real pain. So we're just going to consider in this course a stationary target. So we have some ball like this. Once again, this is a lot like billiards, right? This is the before, and this is the after. What you have is some ball moving up here. So this is what we'll call mass 1 again. This we'll call this mass 2. After it collides, we're going to say mass 1 goes down and mass 2 goes up, and it has some angle theta 2, and mass 1 has some angle theta 1 relative to our initial system. So just to keep in mind, we're going to only consider stationary targets. We have one ball that's moving along. Because it's just one ball moving along, if it was moving like this, then we would just change our reference frame, right? So that this was the x-axis. We just want to keep our life as simple as possible. If it's not stationary, this is a much harder problem. So if we're just going to assume the situation is a ball comes, strikes this ball, and then moves off like this. Okay, so how would we do this? First of all, what's the initial momentum? Yes?
I just need views on what the data here.
Okay, good, thank you. So what we have is, we're just defining this to be the x-axis. We're defining this to be the y-axis. We're assuming that these balls are coming in along the x-axis, and then they're striking here. Now this, what we're saying, once again, is we have some x-y coordinate system, and this angle is relative to the x-axis. This angle is relative to the x-axis. Okay, good question. Any other? If you're ever confused, don't hesitate to ask, because there's some things that I just probably ought to explain a little bit better. So anyway, this is always relative to the x-axis or the initial axis in which these balls struck each other. The reason why we're doing it like this, right, if this ball had come in and struck this ball this way, then what I would do is if let's say the ball is coming here and it strikes this one, then I would define this as being the x-axis, just because that makes my life a lot easier. Because I want to basically consider the initial momentum in one dimension, and then the final momentum I can define in terms of that initial axis. So what we say is along the x-axis, what do we have? What was my initial momentum along the x-axis? M1, V1I, right? M1, V1I. That's my initial momentum along that x-axis. What is my final momentum along the x-axis? Say? Okay, so I'm going to have M2, V2. So this is my velocity vector going off like this, right? V2 cosine of theta, right? Since the cosine is the projection of this vector along the x-axis, right? So if this is the velocity vector here, this is theta 2, right? This is V2 final. then I want to find the amount of V2 final in the direction of the x-axis, which is V2 final cosine of theta. Okay? So I have M1, V1 final, and I'm going to take the cosine of theta 1 plus M2 V2 final cosine of theta 2. So that's along the x-axis. Now how about along the y-axis? Sorry? The initial momentum is 0. Good. So the initial momentum is 0. What else am I going to get? So how about the final momentum? Yes? Excellent. Okay, so we're going to have M1 sine theta 1, M1 V1 sine theta 1, but this is a negative angle, right? So the sine of a negative angle is the negative of the sine of that angle, right? And then this is going to be a positive angle. So I'm going to get minus M1 V1 final sine of theta 1 plus M2 V2 final sine of theta 2. And just remember, so here's what I was saying earlier. The sine of minus theta is equal to minus the sine of theta. That's all that is meant there. So I'm just taking the magnitude of sine theta 1 here and using that in this equation. Okay? So, and lastly, so this gives us the x-axis, this gives us the y-axis, and we have one more equation to consider, which is simply the sum of the kinetic energies have to be equal, which is M1 V1 initial squared is equal to M1 V1 final squared plus M2 V2 final squared. So we have three equations, and that's enough to solve everything here. Okay, so lastly, I want to talk about something that's pretty neat, which is rockets. Then I want to give you a cool example of a Saturn V rocket. Okay, rockets. Why do rockets work? How do rockets work? Yes. Okay, good. So they're just discharging mass. They're changing the mass. And if you think about it in terms of a reference frame, first of all, we're going to consider a rocket in outer space. We're not going to consider a rocket under essentially working against the gravitational force. That's a harder problem. So what we're going to consider is simply a rocket that is expelling fuel in outer space, where there are no external forces on it. Okay, so it's not much harder. You just have to add in mg, but let's just consider this simple situation where there are no external forces, and what we have is initially we have some rocket, which we'll just call mass m. Okay, so this is the before picture. Now what we can say is is m minus dm. Right? This is the mass that's discharged. I'm just going to draw this as a bunch of particles out the back. Okay, this is a small amount of mass that's discharged back here. But now, this was originally going at velocity v, but this is now going to go at v plus dv. So the ability to discharge these particles allow this to go at a higher speed. If you want to just think about it in terms of the center of mass, right? What you've done is you've gotten rid of these particles. Now, the thing I want you to think about here, this is a really important concept. What we're interested in is the relative velocity of the particles coming out of the back of this. Because this rocket, let's say this rocket is moving at 10,000 meters per second. And I think about the fastest propellant that you can get for a rocket. I'm not a rocket scientist, so I don't actually know. But I think it's about 4,000 meters per second. So if I'm moving at 10,000 meters per second and I'm discharging this at 4,000 meters per second, what is the speed of the discharge relative to a frame that we would call stationary? It's still moving at 6,000 meters per second. So what's important isn't the absolute velocity of the discharge coming out of the back, but the relative velocity compared to the rocket. Right? So if this rocket is moving super fast and it's discharging something out of 4,000 meters per second, that discharge relative to what we would call a stationary frame can be at very much different speeds. Right? If it's moving really fast, that discharge can still be moving very, very fast relative to the stationary frame. And if a rocket goes by past here at 10,000 meters per second, we would see the discharge go very, very fast. Or we'd see the discharge moving at 6,000 meters per second. But compared to the ship, it's moving 4,000 meters per second out the back. Okay? So let's think about that for a moment. So let's just think about the velocity of the center of mass. Initially, the momentum was mv. Right? So that's our initial momentum. That is the before. The initial momentum is mv. Now we have two parts. We have something with reduced mass moving at v plus dv, and something that's dm moving relative to this rocket at some velocity back here. Okay? So let's write that out. So my mass now is m minus dm. And what's my momentum? What's my momentum of this rocket now? Okay, so m minus dm, v plus dv, right? That takes care of the rocket, but how about the discharge? Well, the discharge is, plus we need to figure out the mass of the discharge, which we call dm. dm just means the small amount of mass that we've discharged from the system. dm plus v plus dv minus velocity relative. Right? So this rocket has increased from v to v plus dv, but it's discharged. But now the velocity of that mass coming out of the back is what we would call velocity relative to this, which we would say is the velocity of the relative to the ship moving away. All right? Now, you can see here, so we have a lot of stuff. I realize it's a lot of stuff here. But let's look at it. It's actually not too bad if you look at it all together. So I'll just write it out again. mv is equal to m minus dm v plus dv plus plus dm v plus dv minus v relative. Okay, so if we look at all of this and start adding and multiplying things out, let's just say we have m times v plus dv. Oh, sorry. I want to get rid of this for a second. So I want mv. I have an mv here, and then I have plus an m dv minus dmv plus minus dmdv, and then we have a plus dmv plus dmdv minus dmv relative. Okay, so this mv and this mv cancel out. So I'm just going to connecting line here. Okay, those are the same thing on opposite sides, so those cancel out. Then we have a dmdv and a minus dmdv and a plus dmdv. So I can cancel those out. Then I have a dmv, a minus dmv here, and a plus dmv here. And I'm left with dmv relative is equal to mdv. So that was a lot of math just to find out that we end up with this right here. But what is this? If I divide by dt on both sides, what is this? What is dm dt? What is dm dt? Think about dm. What is dm? dm was the amount of mass discharged out of the back, right? It is the change in the mass of the rocket. What is dm dt? Right, it's the rate at which the rocket expels propellant out the back. Right, this is just a rate. The rate at which propellant is expelled times the velocity that it is expelled. So, for example, as I was telling you earlier, it may be 4,000 meters per second. Right? So this is the rate at which it's expelled. This is the velocity which is expelled. And then this is equal to, oh, did I miss a minus sign here? I think I'm supposed to have a negative here. Let me just check. No, okay. Sorry, that makes sense. Okay. No, I am supposed to have a minus. Where does it go? Velocity relative, mdv plus. Well, I don't know where my minus sign went, but I have a minus sign there somewhere. Sorry, I have a minus sign error somewhere. So what you can think about, this is the rate at which it's losing mass, right? So what this is saying is this is the rate at which it's losing mass. But this, sorry, I have a minus sign somewhere, and I'm not sure where it is. I'm sorry. I apologize. But the important part is this is the rate at which it's losing mass, and this is the velocity which the mass is being expelled, and this is dv dt. I will correct this next time and figure out where I made my mistake. Yeah.
You didn't bring the negative sign for TM. Or no, that's zero. Would it be because the velocity is in the other direction for the TM?
I don't know. I'll have to think about it for a minute. I'll have to think about it and then get back. So, but this is the important part. I have the rate at which mass is being discharged, that's why it's negative, times the velocity here, and that's equal to its mass times acceleration, which is just the force. In other words, the thrust, or the force, is equal to the rate times the velocity at which it's discharged. Okay, so if I look at this, and I do a calculation, so I just did the Saturn V rocket. The Saturn V rocket discharged, so it discharged about 2.2 times 10 to the 6 kilograms in, so the mass discharged is 2.2 times 10 to the 6 kilograms in 150 seconds. So this ends up being about 15,000 kilograms of discharge per second. And I believe the relative velocity was a little over 2,000 meters per second, which gave a thrust of about 34 million newtons. So it was a pretty impressive rocket. So that was the Saturn V. Now I want to show you one more calculation, which is how can you determine how fast it's going after it's discharged a certain amount of mass? So we have this mdv is equal to v minus v relative times dm. This means that dv is just going to be equal to minus v relative integral of dm. So if I integrate both sides, so I go from my initial velocity to my final velocity, goes from my initial mass to my final mass. This means that the velocity final minus velocity initial is just going to be equal to minus v relative, and this is, oh, sorry, I forgot to divide by m here. I get the log, natural log of m final over m initial, but I can simply take this negative, flip the logs, and I see that this is velocity relative times the natural log of m initial over m final. So at any one particular time, if I assume my initial velocity is 0, then I can just say, what is my initial mass compared to my final mass? Take the log of that and the speed at which the particles are being ejected out the back, and I can determine the velocity at any function at any point in time. Can everyone see that? Too low on the board. So let me just say velocity final minus velocity initial is equal to v relative natural log of m initial over m final. Okay, so had Saturn V been launched in space, then we know the initial mass, we know the empty mass, We know that the rate at which the fuel is being discharged, and so we can find the final velocity. Of course, we're working against the gravitational field, so it's not quite that easy, but it is a very. I'll find my minus sign here and get back to you on that.